Hi everyone, welcome to our lecture on faults and failures. This is going to be a relatively quick lecture. We'll start by going over some definitions of what failures are, what faults are, what classifications we have, and then we'll talk about some specific types of failures as well as external faults that are common in power systems. Now, before we get started, let's remember where we are. We're discussing hazards as part of the broader framework of risk management. So essentially, we're discussing this part of the framework. What are the hazards and threats to the power systems? And as you know, and as we have talked about it quite a few times throughout the semester, these hazards would then, under favorable conditions, would turn into a hazardous event, and then different hazardous events through various accident scenarios would lead to consequences which we would then consider in order to be able to quantify the risks imposed on the power system. And again, the path from a hazardous event to different end events that are consequences would be through a series of pivotal events, as we have seen in event sequence diagrams. So we are talking about different types of hazards, and failures and faults are one of the most important categories, not just for power systems, for any engineering system. Let's start with some basic definitions. A system is a combination of components and subsystems that together form an entity that works and interacts with other systems or other entities. Every system has a functional specification and provides a certain functionality subject to certain performance requirements. And the way a system implements that function is known as its behavior. Now, systems as a whole or individual components that belong to a system are typically exposed to potential failures. It is important to have an understanding of what a failure means. Failure is defined as the termination of the ability of a component to perform as specified. Based on this definition, failure is an event. It's an event that takes place at a particular point in time. Now, there are different types of failures. A failure can occur in a passive state, which is not going to be evident to us until this item, this component, transitions to the active state. In that situation, we will then notice the failure in the form of a non-ideal performance. Let me give you an example. Imagine you have a light bulb that is exposed to some vibrations, and because of the vibrations, the filament might get damaged. If this light bulb is off, the filament might get damaged due to the vibration, but there's no way for you to know about that. So this is going to be a failure in a passive state. This failure is going to be hidden from you. But then next time that you turn on the light bulb, it's not going to work, and the fact that it has failed will reveal itself to you. Failures can also be classified as active or latent. Active failures are failures that trigger some follow-up events that are unwanted. An example of an active failure would be an error by a human operator that would lead to certain follow-up, faults and failures. On the other hand, a failure can be latent. This is a type of failure that lies dormant in the system and doesn't necessarily lead to any type of unwanted events, but in the future, if certain circumstances are met, it might lead to a particular event in the future. Some examples of latent failures are, for instance, poor design, or failure in maintenance, or, for example, operational procedures that are poorly defined. So these do not necessarily lead to a particular event in the future, but if the circumstances are right, they might. Failures have causes associated with them. A cause is defined as a set of circumstances that would lead to a failure. There are a variety of potential causes for failures. These could be things that happen during design and specification stage, during manufacturing of the component, or the way it's being installed, or the way it's being operated, or during maintenance. And it could be an action, for example, an action taken by a human operator, an event like a shock from outside world, a stressor from outside world, or any type of operating condition. So different things can lead to a potential failure. Now, we typically classify causes into two categories of proximate cause and root cause. Proximate cause, which is also known as the direct cause, this is an event or a condition that happens immediately before the failure. So typically, this is not the root cause of the failure. Root cause, on the other hand, is the main factor that contributes to that particular failure. So typically, the way it works is that you have the root cause, and then this root cause will lead to certain events or certain conditions through like a chain of events, and eventually it gets to the proximate cause, which then leads to the failure. For example, imagine in a power system you have a short circuit happens between two overhead lines, for example, line-to-line short circuit. This short circuit is going to be a failure. However, the proximate cause of the failure could be, for instance, that one of the phases, for example, this phase, gets closer to the other phase, violating the safety clearances. Now, this is the proximate cause, the immediate cause that led to that failure of short circuit. But what are the root causes for this? The root causes could be different things. For example, this could happen due to conductor galloping, which could be as a result of high winds blowing in that area. Or, for example, this particular phase, let's call it phase A, might be overloaded, meaning that the additional thermal energy due to ohmic losses would lead to the additional sag of the conductor. Hence, this particular phase will get closer to phase B, leading to that short circuit. So proximate cause, to recap, is the direct cause immediately before the failure. Root cause, on the other hand, is the main cause that has essentially initiated that chain of events that has led to the failure. Now, failures can be classified in different ways. This is one type of classification in which we look at failures in terms of first intermittent failures and extended. Extended means that it will continue for a long period of time. Intermittent is a type of failure that happens and then it goes away, perhaps even on its own. Extended failures, which are more of interest to us, could be complete or partial. Complete extended failures are failures in which the main functionality of the component is lost. Partial, on the other hand, it means that the functionality is not lost. The component can still operate, but perhaps not within the specifications, the intended specifications. Now, each of those complete or partial failures could be further divided into sudden or gradual events, and there are specific names for a sudden complete failure and a gradual partial failure. A sudden complete failure is known as a catastrophic failure, and a gradual partial failure is known as a degraded failure. Failures can also be classified according to the cause. One class is the primary failure. This is when the component is being used in its intended operating mode. And for different reasons such as aging or non-ideal properties of subcomponents, we will have a failure which would lead to a fault condition or fault state for that item or component. Another class is the secondary failure. This happens when the component is being used in its intended operating mode. However, it's being under additional stress or overload conditions. Now, that stress or overload, which could be anything from external world, the environment in which the item is being used, or any type of shocks that are applied to it from the outside world, could lead to that secondary failure, which would then lead to a fault condition. We also have a class of systematic fault. These occur due to systematic causes. which could be because of human error or any type of errors in design and specification, in operation, in installation, in maintenance, and any one of these types of conditions could lead to a systematic failure, which would then again lead to a fault state for that component. The important thing about these systematic failures is that you have to have the systematic fault, but you also need to have some sort of a trigger. So typically without a trigger, that systematic fault is not going to lead to a systematic failure. We also have a security failure class in which an item or a component fails because of a deliberate human action. And for this, you would need to have the combination of a threat. You would have to have a threat actor, for example, the cyber intruder or the terrorist, and also vulnerability for the component. When all three are there, you have the vulnerability, you have the threat, and an actor who will act on that threat, you would then have a security failure that would lead to the fault condition of that item. In power system studies, fault has a specific meaning, often refers to a short circuit situation. In reliability theory, however, fault has a broader meaning. Fault is defined as an abnormal condition or defect at the component or subsystem level, which may lead to a failure. So fault is something that could lead to a failure. A fault can be dormant, meaning that it doesn't lead to an error, or active, meaning that it does lead to an error. And what is an error? Error occurs whenever the external state of the system deviates away from what is the desired service or the specified service. Similar to faults, errors can be detected or can be latent, meaning that they are present but they're not detected. And what that means is that they are not reflected in the external state of the system. If they're not reflected in the external state of the system, you're not going to be able to observe them. So those will be latent errors. There are different types of classifications for faults. This is the one classification that I like the most and what we will be using in this course. According to this classification, there are three types of faults. One is external. This is basically any event that is external to the system, and you can think of it as a shock that is applied to the system from the outside world. Then we have systematic faults. Systematic faults occur without any prior item failure. And essentially it's due to some sort of human error or any type of error during the design and specification of the component, during its manufacturing stage, transportation to the site, installation, operation, or maintenance, for example. These types of faults can be viewed as internal to that component or to the system. Some examples of it could be, for example, design errors, installation errors, or software bugs. The third category is the failed state. This is essentially a fault that is a consequence of a failure, and I'll talk more about that on the next slides. Okay, this diagram can help you put things into perspective. Imagine you have two components that are interconnected, components A and component B. Component A might fail due to a variety of different reasons. For example, there could be an external fault. Think of a lightning, think of an earthquake, think of any other type of natural hazard, any type of shock that is applied to component A. Or, for example, some sort of an internal fault, which, as we saw in the previous slide, is a systematic fault. Now, either one of these can lead to an error. As long as this error remains internal and is not viewed in the final functionality of the component, it's not going to cause the component to fail. It might be just an internal error that propagates into different subcomponents or sub-items, and it goes into different directions until, for example, it affects the final functionality of component A. When this happens, when the error reaches the output functionality of component A, all of a sudden component A goes from providing correct service to incorrect service. And this is when the failure occurs. And as we talked about it a couple minutes ago, failure is an event that happens in a particular point in time. So when your service goes from correct service or correct output to incorrect service or incorrect output, that's when the failure takes place. And this failure would then be sort of the external fault to component A, which would then lead to errors propagating throughout component B's sub-items and sub-components until it reaches its output functionality, causing it to fail. So here we're really looking at all three types of faults. One of them is the external fault. The other one is the internal fault that we called it systematic fault, and the third one is the failed state, is the fault which is the result of a failure. Now, in order to put this into a kind of a better perspective in terms of the relationship between the third type of fault, which is the failed state, as a consequence of failure, think of this diagram. Imagine you have an item that is operating through time, and it has a particular range of acceptable performance. So as long as, let's say, whatever output of interest that we have in mind, as long as that output lies within this range, we assume that the component is operating correctly and everything is fine. The moment that the output of that component goes outside that acceptable range, this is when the failure takes place. And again, remember that failure here is an event. The failure takes place, the item goes from a healthy state to a faulty state. So fault in this case would be a state. This is the third class of fault that I presented to you, which is the failed state. Okay, now that we know the basic definitions of failures and faults, let's talk about a very important aspect of reliability theory, and that's dependent failures in interconnected systems. In most simplified analysis, when you have a system that consists of multiple components, you often assume that component failures are independent, meaning that if one component fails, it has no impact, positive or negative, on the chances or likelihood of failure of other components. While this is okay in simplified analysis, the assumption may not be true in real life. So in a lot of situations, if one component fails, it can have some sort of an impact on the failure rate of other components, either positive or negative. Within that context, we think of 4 different types of dependent failures: cascading failures, common cause failures, common mode failures, and negative dependence failures. Our focus for the rest of this lecture is going to be on common cause failures for the most part and negative dependence failures. Cascading failures, we'll just touch on it very briefly today, but is the topic of one of our future lectures. And common mode failures are essentially a very special class of common cause failures in that different devices that are exposed to a common root cause, they fail in one particular mode. Okay, let's talk a little bit about basics of dependent events and dependent random variables. Imagine you have 2 events, E1 and E2. These are statistically independent if probability of E1 given E2 equals probability of E1, and probability of E2 given E1 is equal to probability of E2. What is it trying to say? This is trying to tell you that probability of E1 happening, given the fact that E2 has already occurred, is equal to probability of E1 happening, meaning that the fact that E2 has already occurred has no impact whatsoever on the likelihood of E1. When this is true both for E1 and E2, we will say that both events are statistically independent. Another way to show this mathematically is for independent events, probability of E1 and E2 is essentially probability of E1 times probability of E2. If the two events are not independent, obviously they are assumed to be dependent. Now, it is possible that E1 is dependent on E2, but not the other way around. However, if both E1 is dependent on E2 and E2 is dependent on E1, then we will say that the two events are interdependent. Now, dependency among events or failures, which is the event of interest in reliability theory, could be positive or negative. If the probability of E2 given E1 is greater than probability of E2, it means that when E1 happens, likelihood of E2 happening would be higher than if E1 does not happen. So that means that E2 is positively dependent on E1. E1 happening has a positive impact on likelihood of E2 happening. And as you can imagine, the reverse is true as well. If by the fact that E1 has occurred, we know that probability of E2 happening now is less than, in general, probability of E2 happening, it means that E1 has a negative impact on likelihood of E2 happening. So E2 is negatively dependent on E1. Now, one thing for you to think about is in probability theory, we know of mutually exclusive events. These are events that cannot happen at the same time. So I'd like you to think about this. Can mutually exclusive events be independent? What I'd like you to do is to pause the video at this time and think about this a little. And when you're ready to move on, just hit play. Okay, so assuming you've thought about this, you know that probability of two mutually exclusive events happening is 0, meaning that if E1 and E2 are mutually exclusive, they do not happen at the same time, so probability that both of them will happen would be 0. At the same time, we know that for independent events, probability of E1 and E2 would be probability of E1 times probability of E2. Obviously, these two are not necessarily equal to one another, meaning that mutually exclusive events cannot be independent. And this is a very important conclusion when it comes to understanding dependency among different events. Okay, let's move on to the different types of dependent failures. So one of the important types of dependent failures is cascading failures. As I mentioned, this is a topic of one of our future lectures, so we're not going to be talking a lot about this, but just so I give you a flavor, cascading failures indicates situations in which failure of one component results in the failure of another component, and when the second component fails, the third one will follow, and the fourth one will follow, essentially creating some sort of a domino effect. This typically, mathematically, we can say that cascading failures occur when failure of a component increases, or the likelihood of failure of a component increases when another component has failed, meaning that probability that x1 is 0, x1, imagine this is the indicating the failure of a particular component. So the probability that component 1 fails, given that component 2 has already failed, is higher than probability of component 1 failing, given that component 2 is operational. Meaning that if component 2 fails, it will increase the chances and likelihoods of component 1 failing. If mathematically we have this criteria met, it means that the conditions are set for some sort of a cascading failure. There are a lot of situations in power systems in particular when cascading failures may occur. One of the very, very common situations is where you might have a bunch of components that are sharing a particular load. So imagine you have two buses and you have, let's say, three parallel transmission lines. So here you have a generator and you have a load area. If one of these lines fails for whatever reason and is opened, that means that the entire load, which before was split three ways, would now have to be divided between the remaining two lines. So that means that the remaining two lines are likely to be overloaded, which is some sort of a secondary failure category, and it's very possible. I mean, if it exceeds the ampacity of the line, it's possible for one of the lines to trip as well. When the second one trips, all the load is going to be now dumped on the remaining line. So in situations like this, you will have failure of this guy, which leads to failure of this guy, and failure of this guy, which would be an example of cascading failures. Another very common type of dependent failure is a common cause failure. This happens when you have multiple components that are exposed to a particular shared cause, and they fail as a result of that shared cause, either at the same time or within a short time interval. This shared cause could be a shared shock that is coming from the outside world. For example, you have lightning activity in a region and pretty much all your parallel lines are going to be exposed to that, or a storm, or a tornado or something like that. So that would be a shared shock that affects all those components. Or you could have a common stressor. For example, vibration in the environment, or an excess humidity or excess temperature in an environment that affects all the components the same way. Common cause failures are, have been traditionally studied in nuclear power industry, in aviation industry, and recently in offshore oil and gas industry. And they're mainly related to redundant structures that are known as K out of N. This is spelled as K out of N, meaning that this is a system consisting of N components. If K out of these N components work fine, the system is going to be operational. If more than K, if less than K components are operational, the system will fail. Now, in order for a failure event to qualify as a common cause failure, two conditions have to be met. First, the components must be in the failed state at the same time. They don't necessarily need to fail at the same time, but they have to be in the failed state at the same time. And second, that particular fault that is due to the shared cause must lead to the failure of the entire system. For example, if you have a 2 out of 4 structure, this is not a 2004, this is, you say it as 2 out of 4. If you have a 2 out of 4 structure, that means that you have 4 similar components. If 2 of them work, the system is going to be operational. In a situation like that, if 2 components fail, even if they fail due to a shared cause, this is not known as a common cause failure because the whole system has not failed yet. But if three of the components fail due to that shared cause, then this would be a common cause failure. Now, the causes for common cause failures are classified as the shared cause or the root cause, as well as the coupling factors. The shared cause is basically the common stressor, the common shock that is applied to all the components. So this is the main cause that leads to the failure of individual components. But because in common cause failures we have to have multiple components failing as a result of that shared cause, that means there should be some sort of a coupling factor between these components, making them interdependent and interrelated as it comes to the shared cause. So these coupling factors, there are a lot of examples for it. For example, components that have the same design. So if there is a vulnerability in one design, pretty much all the other components that have the same design might fail. The same hardware, the same software. If there is one bug in one of the software systems, since all components have the same software, all of them are going to be experiencing the same bug. or if you have multiple components that are connected to the same network, or for example, they have been installed by the same people incorrectly, or they have gone through maintenance by the same maintenance staff incorrectly, or they're exposed, or they are located in the same environment, the same location. So these are the coupling factors. So essentially, you need to have some sort of a shared cause, and you have to have coupling between these components in order for common cause failure to occur. The last class of dependent failures that we talk about is negative dependence. This is less common than positive dependence, but essentially it talks about a situation in which you have a series of components, and when one of them fails, its failure will lower the chances or the likelihood of failure of other components. Imagine, as an example, that you have a series of, for example, semiconductor devices that are operating in the vicinity of one another, and one of them has some operational issues or some design issues and is creating a lot of excess heat. Obviously, other devices that are in the vicinity of that device will be exposed to that heat and are likely to fail as a result of that increased temperature. However, if this one fails, that source of excess heat will go away, so chances of failure of the remaining devices will be lowered. This is an example of negative dependence. Or as another example, imagine you have a line and you have a fuse here and a bunch of, fuses on the laterals and, other devices such as, potential transformers, current transformers, things like that. If this fuse fails open, then what happens is the downstream circuit is going to be de-energized. When it is de-energized, it's not going to fail anymore. A component that is de-energized is just going to remain de-energized. So this means that failure of this guy will reduce the chances or the likelihood of failure of other devices. So that's an example of a negative dependent failure. Now let's shift our focus to a new yet related topic of system trustworthiness. A system might consist of a lot of subsystems or components or subcomponents. Now, when one of these components fail, for example, it's possible that the entire operation of the system is not going to fail. However, it is likely that some of the features of the overall system might get affected. So one thing that is interesting for us to know is if I have a partial failure within that system, for example, one of the components has failed, or borrowing the terminology that we talked about before, you have an internal error somewhere that has not led to the output of the system yet, but it's somewhere inside the system. I would like to know how this error, how this partial failure of one of the components is likely to affect the overall performance of the system. This is known as the trustworthiness of the system or the trustworthiness of a component. And it's a relatively well-established topic in computer science, but has not been explored that much in power systems. So one of the things that we would have to consider is as systems become more complex, more interdependent, more interrelated, it's possible that the failure, either complete or partial failure, of one of the components within one of these systems is going to be propagating throughout the entire network of these interconnected systems. This is something that we refer to as the fault propagation within a series of systems. Now, I would like to know how trustworthy the remaining systems are, meaning that do I have to shut down everything and go ahead and, for example, repair or replace that one faulty component, or can I continue operating the system as is, just keeping in mind that, for example, I'm not at 100% capacity anymore. Now, one way to implement trustworthiness analysis of an overall system is to look at individual components within that system and how they are interrelated with one another. And identify the trustworthiness of individual components, this guy, and then depending on how normal or abnormal it is, identify how that abnormality, for example, would affect the overall performance of the system, or what other parts of the system are likely to be affected. Luckily for us, IEC 61850, which is a very important standard related to utility automation systems, defines some attributes for individual objects, physical or logical objects, so that we can identify either the physical health of different components or the integrity of the data or services that are provided by them. One, for example, is the logical node health. This is within the context of IEC 61850, this is known as the logical node. But you can think of it as an attribute associated with that particular component. One is logical node health, and the other one is physical health. So health is basically indicating the state of that component. It could be related to the hardware or the software of a particular component. And it has categories of OK, meaning that the component has no issues, warning, which is it has some minor problems, but it's still operating in the safe mode, or alarm situation, which is the component has severe problems and is not operational. Likewise, we can have physical health, which is kind of the same concept, except that it refers to the physical aspect of the device. Similar to that, we have data quality. That's again another logical node within IEC 61850. And this attribute indicates the quality of the data or services provided by that component. And it has some categories. One is validity, which you can say, for example, the data that is being provided to me by a potential transformer, for example, or a current transformer, is good, is invalid, or is questionable. And if it's invalid or questionable, then you can kind of detail what the issues are through an enumerated list. For example, there is an overflow in the numerical value. The numerical value is out of range, or it's against a bad reference, or it has been oscillatory, it's going up and down, so I cannot trust that value. Or other things. For example, the data has been inconsistent or has not been updated for a long time. So that basically gives you additional information related to why that data provided by the device is questionable or invalid. We use this concept in an interesting case study, and we demonstrated it for a particular, like a small scale distribution feeder. So imagine you have this feeder here, you have your distribution substation, this is your transformer with tap changer, and then you have various voltage transformers and current transformers that are connected in different places. You have fixed and switched shunt capacitors, you have a couple of DGs, and then you have some voltage transformers, one here and one here. And I'm assuming that I'm implementing different functions for this feeder, and these functions are, I'm trying to optimize the dispatch of those DG resources. I'm having an application for electric service restoration if anything happens to this feeder, so we can supply the loads from other alternative sources and alternative routes. We have voltage VAR control in order to regulate the shunt capacitors and voltage transformers, and also I have conservation voltage reduction, in which I try to lower the node voltages in order to reduce the demand. So these are the different functions that I have, and these functions for their successful implementation, they rely on the data that is coming from the feeder, and the data is coming from the feeder through VTs and CTs, and then once I receive the data and process the data, I will then send commands back to physical devices such as voltage regulators and switch shunt capacitors and the DGs. So in this system, and I'm not going to go through the details, but what we did was we developed a map of interdependencies between different components. So as an example, we said that for conservation voltage reduction, you will be connected to HMI, the human machine interface. You will be reading data from VT number 6 and VT number 7, the voltages, and then you also exchange information with the OLTC, the tap changer, with that transformer at the substation, and you will send and receive information or share information with the voltage VAR control module. Likewise, the voltage VAR control module works with the capacitors, with the switched capacitors, with reads information through the different voltmeters, and things like that. So what we did, and again, I'm not going to go through the detail, I just want to give you a sense of what that trustworthiness analysis would look like. And what we did was we said, okay, imagine one of the switches has been compromised, meaning that there has been a cyber intrusion event affecting that particular switch. My question would be, now that I know this switch is compromised, is not trustworthy anymore, does it mean that I have to shut down the entire system? Or can the system continue to operate? In other words, bringing it back to the notion of, to the context of reliability, does the system completely fail, or does it go through just a partial failure and I can continue operating at least parts of it? And through that map of interdependencies, what we realized is that if the data quality, for example, that is provided by this guy is low or invalid because of the cyber intrusion, then these are the list of devices and components whose behavior would be impacted, meaning that you have to be very, very careful. And I used a color code of red, meaning that the application or the component has to be shut down. It's not trustworthy at all. Orange means that it's a warning situation. It's likely that its functionality is compromised. Yellow meaning that it can continue operating, but you have to monitor that closely. And green meaning that everything is fine and that component has not been affected. So through this visual representation, you can see that if one component goes through a complete or partial failure, there are certain other components within that system that will go through perhaps full or partial failure, but the remainder of the system will be completely okay. So this will be from the system's perspective, would be a partial failure, and the system, or at least the green parts of the system, are still going to be trustworthy. Okay, now let's shift our focus to external faults in power systems. So far we have really talked about failures and faults in a kind of a broad sense and quite general that could apply to any type of engineering system. But let's focus on the external faults in power systems. So again, to remind you, we said faults in any system could be external, which is related to an external shock applied to the system, can be systematic, which is internal to the system, or could be a failed state, meaning that there is a failure event and the system or the component will go to the fault, which is a failed state. So here we're going to be talking about just the external faults, the first category. One of the main categories of faults in power systems is short circuits, and these are basically due to different events, different causes, like lightning, animals climbing the poles, or birds, flying in between the lines, or tree branches hitting the lines. And this typically leads to a short circuit situation and high currents. Different types of faults are three-phase to ground, line to line to ground, line to line, or single line to ground. With the latter being the most common one, and three-phase to ground, luckily for us, is the least common one, is the rarest one. Luckily, I say, because it would lead to the highest fault currents that could significantly impact the health and safety of other components. Within short circuits, we also have high impedance faults. This is a situation where you have a short circuit, but the short circuit current is not high enough for the protective relays to kind of pick it up and isolate the faulty circuit. This sometimes happens when you have, for example, a conductor that breaks and comes to contact with the ground, for example. So some fault current will flow to ground, but this is small enough that none of the overcurrent protection devices would pick it up. So essentially, your earth is going to be completing the path of the current. This in particular is problematic if you have a transformer with, for example, a delta configuration or a grounded Y. Imagine this scenario here. If you have this line which is opened and hits the ground, if on the low voltage side you had a YY transformer which was not grounded on either side, then you wouldn't have any currents. But because, for example, in this scenario, you have either a delta Y transformer or a Y delta or grounded Y to grounded Y, through this side, through the low voltage side, you might actually start feeding the fault, and this is known as the backfeed problem. That is sometimes common in high impedance faults. Now, when it comes to external faults, there are a lot of causes for them. This could be lightning, could be contact with trees, could be the internal or external failure of an equipment, could be animals, wind leading to conductor galloping, could be digging if, for example, you're doing construction and you hit an underground cable, vehicle accident to overhead line poles, that's another cause. Ice and snow accumulation could actually lead to two things. So if you have these overhead lines and you have ice accumulation here, the line will get heavier and will sag. So one root cause for one cause for fault or short circuit could be that safety clearance to ground is violated, and then you're going to have a flashover. Or if the weight of ice and snow on the line is too much, it is possible that the tower collapses and the line basically falls on the ground. And vandalism, terrorist activity, cyber intrusions, that can be another cause. Talking a little bit more specific about some of these, lightning is the most common cause of short circuits in the power systems. Typically what we do is we look at the geographical area in which the overhead lines and the transformers and substations are located, and we identify the frequency of lightning activity in that region. One of the numbers that we typically look at is the choronic level, which indicates the number of thunderstorm days per year in that area. This is not a very complete metric because a thunderstorm day is defined as a day in which at least a thunder has been observed. So that means even if you have more than one event, you still count it as one thunderstorm day, which naturally is not very efficient. If you have multiple lightning activities in a day, that would be a more severe situation compared to, for example, just one lightning a day. But this is not reflected in the choronic level metric. The other cause of external faults would be tree branches. There's a variety of different scenarios for this. For example, you could have a relatively big tree or a tree branch that falls on a pole or on a transmission line and essentially, breaks the line open. Or, for example, those branches could be the lighter ones, could be blown by the wind and essentially connecting, the conductors together. And then you will have a short circuit, line to line short circuit. Or sometimes you actually, if you don't do tree trimming, what might happen is you might have a tree in the vicinity of a line and the branches, grow. This is not a good drawing here, but what I mean is you're going to have branches that grow towards the line over time, and at some point they get so close to the line that will lead to a flashover. Animals are another important source of these types of short circuits, especially in forested areas where utilities have their lines through, areas with a lot of trees. They can either climb up the pole, for example, squirrels can do that, and they force a short circuit, or birds would be another possibility. If, for example, they kind of fly between two lines, they might violate the safety clearance. If you have two lines and then you have one bird that is kind of flying in between, you may have a short circuit. Okay, so to recap, what we talked about was the faults and failures in systems, and our discussion was really generic, applies to any type of engineering systems. But what I would like you to do is, as you go back to these slides and the different terms and definitions, think of them in terms of power systems and how they are related to the power grid. So we saw that, just to recap the important things, we saw that failure is an event, is when a component or a system or a subsystem stops being able to provide the services that it is designed for. Failures can be complete failures, can be partial failures, can happen over time, or can be sudden. We also talked about faults, and we saw that there are three categories. Faults can be external to the system, can be internal to the system due to systematic events and conditions, or they could result from a failure. So a failure, which is an event, could lead to a fault, which is a state. These are some references that I used in this lecture. The book by Rosan, this is the main reference for us for risk assessment. He has another book on reliability theory that I used for some of the examples and some of the definitions in this lecture. If you are interested in knowing more about reliability theory, I highly recommend this book, and the third edition is out. It just came out a few months ago. That case study that I showed you about trustworthiness analysis of an interconnected system, this is a work that I did back in 2014, and you have access to this paper through the library. If you're interested, I encourage you to look at it. There's a lot more details in terms of how the network of interdependencies was modeled, and you can basically apply that proposed technique to pretty much any type of engineering system.